Okay, let's go into the set of questions about waves. In our setup, we have a long string attached to a variable frequency generator, so that's this thing here. A 0.625 kilogram mass is hung from the free end of the string, that's over here. The length of the string between the frequency generator and the pulley is 2 meters. We don't know about the length of this bit. Using the frequency generator, we slowly turn the frequency up from 0, so it begins turned off, and we stop it when we hit 1000 hertz. We do end up seeing standing waves on the string, but only for some specific frequencies here. And so our standing waves, the fundamental will look like this, the next wave will look like this, and then it will look like this, and then so on. First of all, find the tension in the string. So the tension in the string happens because this mass is hanging off one end. If we want to find the tension, we know that tension is constant throughout an entire string. So let's draw a free body diagram for M. So here's our mass M. We know that the forces that act on it are the tension in the string acts to hold it up, and the earth pulls it down. That's the force of the weight. We know that the sum of the forces in the y direction, this is Newton's second law, is mass times acceleration in the y. We have the tension points up, so it's positive. We have the weight points down, so it's negative. Equals mass times acceleration. The mass is not moving up or down, so that acceleration is 0. T is equal to the weight, equals m times g. We're given that the mass is 0.625 kilograms times 9.81 meters per second squared. Gives us a tension in the string of 6.13 newtons. We're probably going to start to think ahead here now that we're probably going to end up using the equation V is root T over mu at some point. Okay, so once we have tension, we do tend to think about that equation. Next question. Question 17 now says two consecutive frequencies that produce standing waves are 450 Hertz and 600 Hertz. That means there are no standing waves between 450 and 600. Notice we don't know which resonances they are. We don't know which modes they are. We don't know the n values, but we do know that they're two right in a row. What's the lowest frequency in hertz that will give us a standing wave on the string? So what we're asking with this question is to find the fundamental frequency. There are different strategies to solve this problem. A strategy I like to do is just to start thinking about what are the standing waves on the string. Well, I know that one wave is at 600 hertz. I know that the next lower wave is 450 hertz. So the difference between any two standing waves is a frequency of 150 hertz. So every single standing wave will be generated by a frequency that's different by 150 hertz. So let's make a list of the frequencies that'll happen on the string. So if one wave is 650, the next lower is 450. The next lower below this one is 450 minus 150, or 300 hertz. Got to go down by 150. The next lower would be 300 minus 150 to get 150. 150 minus 150, that would be 0. That's not a wave at all. So this is the lowest frequency standing wave on the string. This one must be the fundamental. Okay, so there's the answer to that question. What is the lowest frequency? 150 hertz. And we might notice here that a difference of 150 matches the fundamental, and that goes with a situation where we have two fixed ends. So these ideas go together. It makes sense for what we expect for the standing waves. All right, what is the wavelength of the longest standing wave on the string? The longest standing wave on the string is the fundamental. Now, we know the frequency of the fundamental, and we'd like to find the wavelength. You might be tempted to use here V equals F times lambda, but we don't know V, so we're going to have to find another strategy. So let's draw the fundamental. We know what that wave looks like. we've got two fixed ends, and the fundamental goes from one node to another node. So this is the complete length of the string. We go from node, antinode, node. That means this is a half of a wavelength. All right, this is giving us a tool to find the wavelength. 1/2 lambda equals L. Lambda equals 2 times L. 2 times 2 meters equals 4 meters. So now we know both the wavelength and the frequency of the fundamental on the string. You could at this point find the wave speed because you know lambda and f. We're not asked for that yet, but if you're thinking about the problem and all the different things you could do, that would be something you could do at this point if you wanted to. All right, our very next question says, as our frequency is varied between 0 and 100, how many times do we get a standing wave? Let's go back to what we did in question 17. In question 17, we already got a list of frequencies, so we know there will be this many for sure. Let's see how many other ones there are. So let's take this list and let's copy that list out again. So we know we've got 150. So my n values of frequency are 150 hertz. Then I've got 300 hertz. Then I've got 450 hertz. Then I've got 600 hertz. For my next higher, I'll have to add on 150. That'll get me to 750. My next, I'll add on another 150. That takes me to 900. If I add on 150, I get to 1050. That's bigger than 1000, so here's where we stop. These are the frequencies of all of the standing waves we see. 1, 2, 3, 4, 5, 6. We will get 6 standing waves. Here, if you wanted to think about your harmonic numbers, this is our first, second, third, fourth, fifth, sixth. So these are the harmonic numbers that go with each of those standing waves. Question 20. Draw the standing wave with frequency 450 hertz. Here's where it helps to have thought about those harmonic numbers. This is the third harmonic, or the third mode, so we know how to draw the third mode. Just as a refresher, n equals 1 is a wave that is the fundamental, goes from node to node. N equals 2 puts another node in there, one right in the middle. N equals 3 is going to squeeze in another mode. So instead of having just one in the middle, we'll put 2 in there. So there are our nodes in this picture. So there's our standing wave where our frequency is 450. For this standing wave, find the speed of the wave. Okay, different ways to find the speed. Let's do v equals f times lambda. We know the frequency. We can use our picture to figure out the wavelength. So v equals f times lambda equals 450 hertz. What about our wavelength? Well, we can get that from our picture. We know that the length of the string is L. That's 2 meters. And if we look, we have a half, 1, 1.5 wavelengths on this string. So for our wavelength, we know that 1 1/2 lambda equals L, or 3 over 2 lambda equals L. So lambda is 2 over 3 times the length, 2 over 3 times 2 meters, equals 4 over 3 meters, or 1.33 meters. Okay, so there's our wavelength. And that gives us a wave speed of 600 meters per second. All right, let's keep going with this question. So I like question 22. It's a great question. True or false? The speed of the standing wave on the string is the same for every observed standing wave. So does that wave speed stay the same, or does it change? If we wanted to think about that, we might remember that equation that we first thought about with the first question we did. We know that wave speed is the square root of tension divided by mass per unit length. The tension T is provided by the hanging mass. That doesn't change, so our tension stays constant. Our mu, our mass per unit length, that's the mass of the total string divided by the length of the total string. That doesn't change either. So as long as our string stays the same, it doesn't change. So our conclusion is that V is constant. It doesn't change no matter what we set the frequency at. So this statement then would be true. Okay, next question. Find the mass per unit length of the string. Here, this is an artifact for having given the question on bright space. Sometimes in a bright space quiz, if you get a previous question wrong, you might get all the following answers wrong. So we gave you, in that old exam, we gave you values of tension and speed just to prevent you from making any sort of subsequent errors based on your previous ones. So this question now says find the mass per unit length of the string. We know the speed and we know the tension. All we want to do is solve for our value of mu. So if V is the square root of T over mu, then we square both sides to get V squared is T over mu. Then we have to cross multiply, so V squared times mu is equal to T. So then we divide both sides by V squared, and mu is T over V squared. It says to use a tension of 9 newtons rather than the value we got previously. And it says to use a speed of 81 meters per second rather than the 600 meters per second we got previously. That gives an answer of 1.37 times 10 to the minus 3 kilograms per meter. Okay, last bit on this section. If the hanging mass in the above question were doubled, would we get more standing waves, or would we get fewer standing waves, or would we get the same number of standing waves? So we have to think about what's the effect of doubling the hanging mass. So let's think about our equation. We know that if we increase the mass, the result of increasing the mass is going to be that we increase the tension because that tension is provided by the hanging mass. If we increase the tension, we're going to end up increasing the wave speed. What happens if we increase the wave speed? Let's remember our equation for the frequencies of the standing waves. That's given by n times v divided by 2l. In our list of waves, as we counted off all the frequencies, our highest n value got to 6. So if we can think about what n is in this new situation, if n gets bigger, we get more waves. If n gets smaller, we get fewer waves. So let's think about what happens to n if we double our mass. So let's rearrange this equation and solve for n. We get n equals 2 times L times Fn divided by the wave speed. Okay, Fn, the biggest frequency we could possibly have is 1,000 hertz. Just like last time, the biggest possible frequency we could have had was 1,000 hertz. So this stays the same, the length stays the same, but the V gets bigger. If V gets bigger, then N decreases. Therefore, we have fewer waves, fewer allowed waves.